Hello, I'm Gordon Bell here at the Computer Museum in Boston. When I got into computing in the late 50s, I met many of the pioneers and saw some of the first computers in action. In fact, the 1952 Whirlwind behind me was the first computer I ever wrote a program for. With this series, I hope to give you a sense of what it was like to invent computing. You'll see and hear the pioneers and their computers in vintage footage and in later day reminiscences. I will be your guide in time travel, from the dawn of computing in the 30s to its commercialization in the 50s. In the 30s, card calculating, while an advance over pencil, paper, and mechanical calculators, was labor-intensive, slow, and unwieldy. Systems like this were used in the war effort, including the design of the A-bomb at Los Alamos. Scientific problems were laboriously done on desk calculators, took hours and days to do, and were fraught with the errors of human input. By 1937, 5 independent researchers were dreaming about computing machines. 4 were driven by curiosity and frustration with the error-prone slowness of their own work. They were inner-driven to build a fast scientific calculating machine. The first was Konrad Zuse in Berlin. While a student of civil engineering, he started to work on the design of mechanical aids to stress calculations. By 1936, Zuse had a basic design for a computer whose operations were specified by a sequence of markings on a tape. The same year in England, Alan Turing's paper on computable numbers was published, introducing the concept of a universal computing machine to an academic audience. But none of the others were affected by his paper. At Harvard, physicist Howard Aiken, inspired by the designs of Charles Babbage, was determined to build a machine to solve nonlinear differential equations that he was encountering in his dissertation. At Iowa State University, John Atanasoff was consumed with building a machine to solve simultaneous algebraic equations for the solution of partial differential equations. And finally, at Bell Labs, George Stibitz was experimenting with the use of relays to build a reliable calculator for circuit analysis. Stibitz was the first to get an operational machine. His story is the BTL Mark I. He tells us about this in a 1980 lecture at the Computer Museum.
There was little effective communication among the computer pioneers, and each development, with possibly one exception, I think, took off from very ancient beginnings. In the case of the relay computers that I had a hand in, the initiation was entirely a matter of curiosity about the way in which relay circuits could be combined and activated. It was just a curiosity about the logical properties of the contacts, which individually seemed so extremely simple, and in collective masses could do some very remarkable things in the telephone business. As I say, this had no connection at all with the need for computers at that particular time. Now, as a mathematical engineer at the Bell Laboratories, everybody was an engineer then of some sort, or else a girl. But I noticed that the relay contact had only 2 stable conditions, off and on, and this I realized was true of the digits in binary notation. Now, nowadays, the binary notation is familiar to most youngsters, and it's hard to realize that in 1937 that I, with a PhD in applied mathematics, had to stop and think back considerably to decide what a binary notation was. I had a vague idea. On looking it up, it became familiar to me again. And we decided to try it out as a means of using the telephone relays. And so late in November of 1937, I borrowed from the lab's scrap pile a couple of U-type relays, and I assembled them as nearly like this as I can remember. And it's designed to add two one-bit numbers. Here is A and here's B. If B is 1, the sum is 1. If A is 1, B is 0, the sum is 1. If A and B are both 1, we get a 1 and a carry and a 0 in the first bit. Took it to Bell Labs and showed to some of my friends down there, and they were satisfactorily amused by the idea that you could use binary notation from the old days to do arithmetic in the modern times. Well, then, I wasn't entirely sure that it was so funny, so I started to think about the possibility of doing a little more elaborate arithmetic than 1 plus 1, and I drew up some circuits at home for a calculator that would be something like a desktop calculator. It's well known that you can easily connect electrical circuits with a soldering iron. You don't have to do a lot of mechanical design to get them to work together. And so I proposed that maybe the relay circuits could be used to do the complex arithmetic. So the project was started in September 1938, and construction began in June 1939. The design work, assignment of relay types, fusing, and all the multitude of details that have to be considered were taken care of by Sam Williams. When I started to think about it, decided against training operators to use the binary notation. But I had considered the alternatives of converting all numbers into binary form inside the computer, or converting decimal digits into binary form at the keys. Now, because of the large amount of input and output we expected from this device, we decided on the latter. That is, each key would convert its own decimal digit into binary form. It was decided that when a meeting of the Mathematical Society was announced for September, that we would demonstrate the machine and give a paper on the subject about why it was useful and how it worked. The original idea was that we would have a telephone line open between Hanover, where the meeting was to be held, and New York, where the machine was, and someone at the meeting would call to the operator on the phone down in New York and ask her to put numbers in the computer and report back what it said. And this scheme was very shortly modified so that the computer would respond directly to a teletype which was located in Hanover and would send data back to that same teletype. Model 1, the complex calculator, was then studied by the group at the Bell Laboratories, and everyone was horrified to find that it had cost $20,000, including the development, design, construction, and debugging. Well, this is a number that simply wasn't thinkable. The idea that anybody should spend $20,000 for a mere calculator was something that was not acceptable, and the labs decided that no more things of this sort would be built.
Soon after the outbreak of World War II, the need for calculation prompted the government to fund the development of more machines at Bell Labs. To give you a roadmap of each of these machines, this graph shows their memory size versus speed. Bell Labs built 6 more relay machines before the end of the war. The largest, completed in 1946, had over 9,000 relays in several rooms, consumed 20 kilowatts of power, used floating point arithmetic, and cost about $500,000, or roughly the equivalent of $4 million today. Konrad Zuse had many ideas that would lead to computing rather than just a better calculator. His 1935 diagram of a universal calculating machine used a punched tape to feed information into a control unit that selected a memory cell and specified the arithmetic unit's operation. He saw the need for large memories as a critical element of the computer because his interest came from civil engineering and performing stress calculations involving matrix algebra. This is an AND gate. The inputs are on the left and on the bottom. When they're both 0, there's a 0 on the output. When the lower input becomes 1, there's still a 0. When the left input becomes a 1, we have a 1 on the output. The Z1, a 1938 prototype constructed in Zuse's Berlin apartment, had a 64-word memory. The Z2 used relays for computation and was useful in convincing Germany's Experimental Aircraft Institute to fund the Z3. The Z3 was completed in late 1941 and operated until it was destroyed in World War II. A copy was made in 1963 for the Deutsches Museum from his 1941 patent application. This model was still working in the early 1990s. Arithmetic was done in a Polish postfix fashion by loading operands into its 2 registers and then specifying the operation. Floating point addition took about 2 seconds. Instructions were read from holes punched on used 35mm film. Other data was read into and written from switches and lights in floating point decimal form. Thus, the controller for doing the floating point arithmetic was non-trivial. Inventing the notation for designing the relay logic was key to the Z3. Zuse himself was very interested in the programming aspects of computation. This talk is from a 1981 Computer Museum lecture.
Surely, at first, I worked on paper, but just right from the beginning, I worked with a floating point principle. I called it to that time the half-logarithmical form, because at first I tried to make computers which were working complete with logarithms. But you know, the difficulty is the addition, yes? I did not succeed to develop a good device for this, from the mathematical point of view, it's clear, yes? Just from the beginning, I was perfectly clear for the engineer. Only a machine with floating point arithmetic will be sufficient. And so, from the first point, I developed my whole mechanical machine with this principle. And only that was the third one. And the arithmetic part was working, but it was not working so sufficiently that it could run day by day, yes, and to make it control it by program. And therefore decided to switch over to the relay construction. And before I did make a whole computer in floating point arithmetic with relays, I made a small test model that was a Z2 that had 16 binary digits with fixed point. I only had in mind to try how works this relay technique at all. I never had in mind this model would work, really work. When I began, I had no knowledge of mathematical and symbolic logic. And I developed for my own purposes, I called it conditional calculus. I had my own science for that, my own representation. I was very proud to have found a new calculus. I sent it to my mathematical teacher of the school. Yes, he was a very clever man, and had contact with him. And I sent it to him, and I got a letter. Oh, what you do there? That's a good old propositional calculus. Yes. And at first, surely I was disappointed. I was proud to have detected a new way. But then I thought, I've got the opinion that it was very good. There existed already a well-proven and elaborated calculus for these things. And I only had to translate the formulas of this calculus into switching algebra. 1936 or 37, when I developed the switching algebra. The machines I had made, Z3 and Z4, may be the most sophisticated wired-in logic which any machine, I don't think that any machine built later on had so sophisticated built-in conditions and so that. I told you that I hesitated to take the wire from right to left, yes? But I put all the logic in the circuitry of this arithmetic unit. And when you solve a quadratic equation, the course of the calculation you can make in a string like Babbage. Only on the end you have two values. And the solution of the square root was perfectly wired in, like division and multiplication and all these things, surely in floating point arithmetic, yes. And so it was not necessary to have a machine with conditional orders to solve quadratic equations. So surely it would have been possible to make conditional orders also to enlarge the machines, Z4, but I saw we were in a hurry. The machine had to be ready. We were in air raids and so. There was not the time to change the principle of the machine. When I would have gone to the people who ordered the machine, the Ministry of the aircraft industry, when I would have said them, well, I have a new idea, I can make it change the address and so on. They would have, oh, you're perfectly foolish, we don't do that. We need only this here. You must be ready next month. When I began with the work in the 30 years, I concentrated my ideas more on the relations between man and machine. I saw that one time there will be that I didn't see any border between calculating and thinking. Surely to that time, the computers we could make to that time, or 20 years ago, they were far away from being electronic brain. Today, I hope you and my brains is ahead of the computers, still today.
The Z4 was constructed between 1942 and 45 and was rebuilt in 1950. Zuse also had to make a living and work for the Air Ministry. Lesser known are his fixed function calculators used between 1942 and 1944 for aircraft design that replaced 30 calculator operators. By 1951, Z4 had a 1,000-word mechanical memory with 1/2 second access time. Its logic was carried out with relays on its 32-bit floating point numbers. It was modified in 1950 to perform conditional branching. It remained in use until 1959. After the war, Zuse started a computer company that built a series of machines before it was ultimately absorbed by Siemens. John V. Atanasoff was perhaps the first to conceive of an electronic calculator using serial binary arithmetic. In January 1940, Atanasoff and his research assistant Clifford Berry built a prototype to demonstrate serial binary arithmetic and the use of a capacitor store. The Atanasoff-Berry Computer, or ABC, was designed to solve 30 simultaneous linear equations to enable the solution of partial differential equations. Capacitors were mounted inside a drum with contacts that were used to read each bit serially as it rotated. Punch cards stored intermediate results. Atanasoff also told his story at the Computer Museum in the fall of 1981.
My mother had a large arithmetic which she'd studied in the 8th grade. It contained many other topics than those usually included in what you'd call arithmetic and what I would call arithmetic. But it had a chapter on numbers with other bases than 10. And I studied this with great care. In partial differential equations, you can't make much progress by trying to solve them. You can't solve them in any ordinary sense. But all you can do is to approximate the answer. There are too many functions necessary to solve those equations. They're all over the map, things you've never heard of before and no one else has ever heard of before, and you just can't get at the solution that way. This is what actuated me really more than any other problem to get interested in the computing art. There I was in 1936, turning my mind to invent a new digital computer, not knowing how it would be built or how it would work. However, I believed that it should be fast, accurate, and flexible. Of what stuff would my digits be constructed? See, we're going to use some quantity to represent digits, and what stuff would that be? And would it be mechanical, electrical, or some other? And what would the structure be? And the only thing I could think of was to separate memory and computing. And maybe it wasn't a bad idea. And now I thought, does base play a role? If we're building a digital computer, what are we going to do about the base? And what determines this? How should I do computing? What was the computer going to be like? And how should memory be constructed? I had all these words at that time, and for base 2 numbers, I thought of a 2-step mechanical system, ferromagnetic material, going back to the wire, you know. And I thought that was an awful good idea. In the end, I didn't use it. A 2-state vacuum tube circuit, and a capacity with 2 states of charge. You should realize that these concepts represented a hodgepodge of ideas. I tried again and again to sort them out. Nothing seemed to work. After months of work and study, I went to the office again one evening, but it looked as if nothing would happen. I was extremely distraught. And then I did something that I did in those days, but I've had to stop lately. I got in my automobile and started to drive. I drove hard so I would have to give my attention to driving and I wouldn't have to worry about my problems. I drove towards the east. I was driving a Ford V8 and with a south wind heater. I don't suppose you know what a south wind heater is. Pretty warm, but the night was very cold. It was in the middle of the winter, 1937 and 38. When I finally came to Earth, I was crossing the Mississippi River, 189 miles from my desk. You couldn't get a drink in Iowa in those days, but I was crossing into Illinois. I looked ahead and there was a light. Of course, it was it. And I stopped and got out and went in and hung up my coat. I remember that coat. And sat down at the desk and got a drink. And then I noticed that my mind was very clear and sharp. And I knew what I wanted to think about, and I went right to work on it and worked for 3 hours, and then got in my car and drove slowly back to Ames. And I had made 4 decisions in that evening in the Illinois Roadhouse. Use electricity and electronics. That meant, of course, vacuum tubes in those days. Use base 2 in spite of custom for economy. Use condensers, but regenerate to avoid lapses. Compute by direct action, not by enumeration. You know, it's an easy thing if you know about number systems to just have things that count, kind of an internal counter that gives you enumeration, but I was going to do it by direct action. The next thing is the Atanasoff-Berry Computer. This represents our main effort in computer construction. It was designed specifically to solve the problem that bugged us, the solution of linear algebraic equations. We're building this machine to solve 30 equations and 30 unknowns, to work on determinants to 30 places. And we're going to use simultaneously 30 abstract mechanisms. On June 13, 1941, Dr. John Markley visited ABC installations at the invitation of Dr. John V. Atanasoff, and he was shown the complete enterprise. Might tell you how things went about that computer. The Iowa State College staff members were not unduly enthusiastic. Corporations were not impressed, and IBM said they'd never build such a machine. Since the beginning, many men have worked on computing, and many have furnished elements that were important. This applies to Markley, Eckert, some members of the staff, such as Burks, Braidard, and others. Historically, the list should contain Pascal, Napier, and Zuse. Credit must also go to the originators of our number system, which began computing. What each man accomplishes depends on his brains and energy, but also on the surrounds in which he works. In this, timing is important. Pascal could not have invented electronic digital computing, although his brain power was overwhelming. In a larger sense, no man invents anything. He builds and extends a little with his friends and on the shoulders of others. Many are quietly involved in making this historical record clear, and we should all support this effort.
When Atanasoff left Iowa in 1942 to become part of the war effort, the ABC still lacked a reliable card punch. It was not in service. The parts were cannibalized, and the only remnant is the drum. Atanasoff's greatest contribution may have been helping break the broad ENIAC patent filed in 1964. He was clearly the first American to use binary arithmetic and vacuum tubes for direct digital computation, and to describe and prototype ideas such as non-restoring divide, a concept the ENIAC patent also claimed. The last stories of this era involve Thomas Watson Sr.'s funding of the Harvard Mark I and the SSEC at Columbia's Watson Laboratory. The inventor of the Mark I was Howard Aiken. Aiken was motivated to build a scientific calculator to evaluate integrals like those he was encountering as a PhD candidate. He alone of these pioneers was inspired by reading the works of Charles Babbage and his plan for an analytic engine. By 1937, he had specified the architecture of a machine that he often referred to as a computing engine. It was the imagination and drive of Aiken that created the ASCC for Automatic Sequence Controlled Calculator, or Harvard Mark I, marking IBM's entry into computation that was not controlled by a plug board. ASCC was engineered, built, and tested by IBM. Operational in January 1943, it was moved to Harvard and dedicated on August 7, 1944. Unfortunately, Howard Aiken died in 1973 and never told his story for the camera. But Rear Admiral Grace Hopper, his co-author of the ASCC manual, vividly describes life working on the Harvard Mark I.
I think we've totally forgotten the environment in which Mark I appeared and what a difference it made in the reaction to her and the problems she ran. 41 was Pearl Harbor. By 43, we were in the thick of things. I had long wanted to join the Navy as well, but I was in a classified occupation. I was a college professor teaching mathematics. At that time, the teaching of mathematics was a classified occupation. However, I finally got permission to leave Vassar, and then I faced a second obstacle. I was underweight. For some unknown reason, to this very day, the Navy considers that I should weigh 140 pounds. And all these years I've been trying to explain to the Navy that I had Scots ancestry and I'm lean and tough and I don't need to weigh 140 pounds. I weighed 105 pounds. My orders sent me to the Bureau of Ships Computation Project at Harvard. This was on a Friday, and I was supposed to report on Monday morning. So I had Saturday and Sunday off with my family, and then I came to Boston. And then I started to find the Bureau of Computation Project. Well, I finally found the Office of Naval Research. They'd heard of it, but they weren't quite sure where it was. So finally, about 2 o'clock in the afternoon, I found the Bureau of Ships Computation Project in the basement of Cruft Laboratory at Harvard. I walked in the door, and Commander Aiken looked up at me and said, "Where the hell have you been?" He then waved his hand at Mark I, all 51 feet of her, and he said, "That's a computing engine." I think when he called it a computing engine, what he meant was it was made up of different parts that performed different functions. He informed me that he would be delighted to have the interpolation coefficients for the arctangent by next Thursday. Well, by this time, I'd have been introduced to the two programmers who were ahead of me. But it was a small group and a very big machine, because Mark I was 51 feet long, 8 feet high, and 8 feet deep, and she was in a magnificent glass case eventually, designed by Norman Bulgettis, which of course made it better than ever. If you go back to that time and to the need for computation, she begins to take her place in history. In the first place, she was the first large-scale digital computer in the United States. She was automatically sequenced. She was programmed, step-by-step program, exactly as we have today. Everybody talks about ENIAC because it was the first electronic computer. But ENIAC was not programmed. He used patch cords and put that together in a simulation of the problem you wanted to solve. It was not programmed when it was built. So that from that point of view, Mark I more closely resembled what we have today than any of those other early machines, because it was sequentially programmed, step by step, one operation after another. There were a lot of adventures with Mark I, some of which have become slightly historical. At the same time we were running Mark I, we were starting to build Mark II for the Navy. And Mark II was built entirely out of relays in an awful rush because the war was on. And we were building Mark II the summer of 1945. And naturally, since it was World War II, we were working in a World War I temporary building. The air conditioning wasn't very good, the screens weren't very good, and the windows were all open. Mark II stopped. They finally found the failing relay. And inside the failing relay, bitten to death by the relay contacts, was a moth about this big. So the operator got a pair of tweezers and very carefully fished the moth out of the relay, put it in the logbook, put Scotch tape over it, and below it he wrote, "First actual bug found." One of the reasons we so greatly needed computation is another thing most people have forgotten. World War II saw an almost complete change in our weapon systems. Up to that time, when you had a mine, the mine had ears sticking out of it. And the ship had to hit the ears and break a connection before the mine went off. All of a sudden, we started building acoustic mines that listened for ships, magnetic mines that waited for to sense the metal of the ships. Well, now we had to know how big was the effect of the mine. How much area was it going to detect ships? So all the computations had to be created to tell us how much space around a mine would this mine affect, so that we know how close to sow the mines, where to position them. So there was a tremendous amount of computation to be done, including the A-bomb and all the other things that happened during World War II. And the pressure for that computation was very great. Everything was hurry up, do it yesterday. So the pressure to keep the only computers we had running was very, very strong. And Mark I ran 24 hours a day, 7 days a week, which was a very rough task for a small crew. Mark I had one set of storage, which was a bunch of switches. It was a big panel. Now, the Mark I word consisted of 24 digits, a sign and 23 decimal digits. So across the panel were 24 switches, and you could turn them to the different numeric positions and put constants into a problem by setting them up in the switches. The instruction was essentially a single address instruction, except I've never seen anybody call it that. Because we wrote in 3 columns. One column was the out column, one was the in column, and the C column was the action column. For instance, a multiply instruction would be 432, out of counter 432, 761 into the multiplier, and 7 to go on to the next thing or whatever. And the in column was essentially the operation to be performed. So it was really a single address code, except that you named the quantity first, then the operation. And the third column was the one that, for instance, would tell a print counter to go ahead and print, or the punch counter to hurry up and punch that card, and so on. Various action codes were in the third column, along with the automatic, which moved it to the next step, which was the 7. So there were 72 of those storage registers, each one of which was an adder. The next important unit was probably the multiply-divide unit. The multiplicand went in first, and then in the registers were built up the 9 multiples of that quantity. The multiplier came in, and it called down the multiples of the multiplicand one after another, and shifted each time and multiplied just exactly the way we do when we try to do long-distance multiplication. So very interesting things started developing, which led to other things later. We began to have pieces of coding in our notebooks. For instance, Dick had a nice little sign program for angles less than pi over 4, positive angles. And when I needed it for another program, I'd borrow it from his notebook and copy it into another program. We didn't realize it, but we developed subroutines. And the whole future of beginning to get the compilers and the various high-level languages came from those things in the notebooks. And both Bob and Dick had notebooks full of those pieces of code. And believe me, I borrowed them very frequently. I also learned another lesson at that time, which later forced me into the development of the compilers, and that was that programmers can't copy things. And that when you integrate a piece of code into another program, you frequently have to add to all the addresses. And programmers can't add either. I don't know whether I've made it clear, but the data and the sequencing were totally independent. Throughout the development of Mark I and Mark II and Mark III, Howard Aiken always insisted that the data and the program must be independent and stored independently. He was a tough taskmaster. I was sitting at my desk one day, And he came up beside me, and I got on my feet real fast. And he said, "You're going to write a book." I said, "I can't write a book." He said, "You're in the Navy now." And so I wrote a book. I have it here with me so that I can manage to answer any questions. This is the Mark I manual, the entire Bible of Mark I. It contains every circuit, samples of all kind of programming, coding. Has an excellent bibliography in it on computation. Has timing charts for all the operations and the various circuits. All the circuit diagrams are in here. You could take this and build Mark I over again if somebody felt like it. But many of the things that we think of today, common, ordinary, or have forgotten where they came from, arose in the development of the first programs that were written for Mark I.
Both ASCC and Columbia's much faster electronic SSEC stand out because they have large memories. Like the Z3, they were programmed from a sequence of instructions stored on tape. SSEC was a prototype for IBM's production model card-programmed calculators. These machines led to important patents for IBM because they could perform arithmetic on and then execute stored instructions. The IBM engineers working on the SSEC went on to build the highly successful IBM 650. The SSEC programmers became members of the IBM 701 programming group, but that's another story. Here's Herb Grosch, one of the programmers of the SSEC.
The heroes of this story are primarily Watson Sr. and Wallace Eckert. This is Tom Watson Sr. as I first met him. He furnished the money, he furnished a large part of the inspiration for the activity through his support for what he thought of as scientific research, what we would today call, I think, applied research. This is the Watson Lab as we saw it in 1945 and 46 when we were moving in. It was a former fraternity house which IBM remodeled at great expense and donated to Columbia University. And it was in those strange quarters that the romantic incidents that I'm going to relate to you occurred. I came into this thing because I was trained as an astronomer. My PhD is in celestial mechanics, and very early in my career as a graduate student, I met many of the figures who were interested in doing this sort of thing somewhat more economically than the old-fashioned logarithm, multiplication table, hand-cranked Brunsviga that had been used for years. One of the chains of applications that made the Watson Laboratory possible was the motion of the moon among the stars. In the early days, we did not have chronometers of any accuracy. In order to determine one's position in crossing the Pacific, you need to measure your longitude as well as your latitude. Without a chronometer, you have to have some other kind of clock. And you can't do it, believe me, with water clocks or sand hourglasses or what have you. Then the war threatened. The U.S. Naval Observatory had to manufacture a new publication called the Air Almanac for the use of navigators crossing the Atlantic by air, and especially for the use of bomber navigation, where the skies were clear and bubble section observations and so on were possible. As a result, they brought Wallace Eckert down from Columbia University for war work, and his war work was to install the first rent-paying installation of Hollerith machines in the world on a continuing basis to do scientific computation. In 1945, in the early spring, there was an announcement in Science magazine that Watson Sr. had called Wallace Eckert back from Washington and had asked him to establish at Columbia University a new scientific computing laboratory. And I wrote Wallace, still I think at the Washington address, and said, hey, can I come around in the evenings and try out some of my ideas on optical design on your nice, new, shiny IBM machines? I did not know at the time that in wartime, even IBM could not get priorities for its own equipment. That in fact, in order to commence this work at that time, and one of the incentives for beginning it at that time was that Los Alamos, which had a special installation of punch card machines doing shockwave calculations and so forth, had run out of capacity. They couldn't find either any more punch card machines that would be maintainable out there on the mesa, or any more people who were willing to move out there to run them. So Wallace had accepted the charge of setting up a shop of IBM machines at Columbia, whose first task would be to supplement the Los Alamos calculations on the Alamogordo burst and some of, but not many of the design calculations for the actual weapons. So while I expected to get an invitation to maybe come around one night a week and play a few games and learn how to run the machines, instead a little man from the Manhattan district showed up at my optical company and took me away. And I said, you know, you can't do that. There is no such thing as a civilian draft. And he essentially said, tell that to General Grove, you know. And the next thing I knew, I was an IBM employee. In the excitement, they forgot to pass me through IBM headquarters. And as a result, although I received an identification card and all that sort of thing, nobody had paused to tell me that you could not have hair on your face and work for IBM. So I not only was a very early scientific punch card operator and supervisor, but I also was the first bearded, sport-coated IBM employee. And this probably has some connection with the fact that I'm the only one in history that they've ever fired twice, bearded or otherwise. Now, as you all know, in 1946, boom, ENIAC. And for the first time, IBM felt threatened by a development that they had not really completely foreseen or understood. Watson Sr. was incensed that someone had produced something that he didn't know about and hadn't sponsored. He had, of course, sponsored the Harvard Mark I 2 or 3 years before, had built it to Aiken specifications, but with completely detailed IBM engineering, had given it to Harvard, and then had been essentially brushed off by Aiken and Conant as, go away, boy, we don't need you anymore. So instead of souring him on the idea of building a big computer, it urged him to build another one which he would not give to Harvard, and which would be as fast and as impressive as ENIAC. Well, he managed to do this within 1 year of the ENIAC announcement. A group of people came together. I still have notes of the initial meeting, and wrote the specifications for this gigantic machine.
The world's fastest mechanical brain. Science unveils an amazing new calculator that solves problems quicker than mathematicians can think them up. This indicator acts as the main control. First problem, computing the position of the moon over a 200-year period. A full-sized mathematical headache.
When Mr. Watson made his final inspection, about 2 days or 3 days before the opening ceremony, he was disturbed at the fact that there were large columns painted a glossy black to make them unobtrusive, marching down the center of the room. And he said, everything is lovely. You gentlemen have done a beautiful job, but I think we should remove those columns. Well, unfortunately, they held the building up, and even for Mr. Watson, they weren't able to do that. However, they did do one thing. They recalled the 4-color brochure, which had been printed for opening day, and not having enough time to reprint it completely, they put out a 2-color sepia print instead, in which the gigantic centerfold showing the picture of the machine room, one which has been reproduced in Datamation and other places, had been retouched to eliminate the center columns.
The inventions we've seen in this program were all created by one person working alone. At home in Zuse's case, at a university in the case of Atanasoff and Aiken, or Stibbets at Bell Labs. All were designed for scientific calculation as distinct from business and commercial record keeping. The federally funded Bell Labs machines and the IBM SSEC were implemented by America's best engineers, unlike the solo efforts of Atanasoff and Zuse. Zuse Z1-3 and Aiken's SSEC were on the main line to the modern stored program computer. Programs were a single linear stream of instructions without branching, however. Computer architects often refer to a design that has a separate store for instructions and data as the Harvard architecture. Historian Paul Ceruzzi has pointed out there was debate about what a computer was and what it should look like. By 1950, there was a common understanding of the nature of the computer, how it should function, and how it should be constructed. The generation of pioneers who worked in the late 40s generally knew about the Mark I and the Bell Labs machines, but neither the ideas of Atanasoff or Zuse had percolated into the mainstream. Many of the breakthroughs that led to fast, reliable, programmable machines were yet to come. These stories are told in the rest of the series. In fact, part 2 starts right here with UNIVAC. From the Computer Museum in Boston, I'm Gordon Bell.